All right, so this is what we saw in the last class, that we took a graph which was actually not completely disconnected, but we could see that it has two communities. So except for this edge from 4 to 8, it should have been two disconnected components. And then we know that the for any connected graph, basically any so the 0 will be one eigenvalue with the constant eigenvector, and then we were interested in the second eigenvector. Okay, and the second eigenvector actually gave us a nice partition into of the graph into two different partitions. So the first 5 were negative, so they would fall into one partition. The second 3 would be positive; they would fall into another partition. And so this we could see that using this method we can actually cluster graphs into two partitions, especially when they look so nice and things like that. So one possibility, of course, was that we could apply this approach iteratively, cluster into two, and then each cluster we take again cluster and so on. And then we said we could actually extend this idea a bit more, and we could apply directly clustering into several partitions. And so that's what we are going to look at today. Okay. So to do that, uh, I'll just give you a brief idea to begin with. Then we'll look at a theorem which is a bit complicated, and then we'll again talk about how we use the theorem. So the idea here is that we think in the ideal case, a network graph should have had disjoint communities. Okay, in the ideal case means in the mathematically ideal case, not socially ideal case. Mathematically ideal case, it should have had disjoint communities so that we could simply block them. We could simply construct the block matrices like we saw previously. But it doesn't happen. So we will use a theorem from perturbation theory, which essentially says that, well, uh, in your idea, if the matrix was ideal, you knew how to do it. Even if it is not totally ideal, slightly distorted, then also the eigen spaces will not change much. And the eigenvalues, the range of the eigenvalues will also not change too much. Okay, so that is the basic idea. So let's actually uh, look at that. So this is a perturbation theorem due to Davis and Kahan. The statement is quite complicated, but I will explain the statement to you. We will not go into the proof of this at all. Actually, the perturbation theory is actually a very important backbone of any sort of spectral algorithm. Many of our ideas of using singular value decomposition for dimension reduction and many other those things are the theory is based on this as well. But anyway, so let's look at this. So the theorem goes the following. Let A be our, so I'll actually also give you the context besides the mathematical statement. I'll give you the context in terms of what it means for our application. So let A be our adjacency or Laplacian. Actually, in our case, it will be the Laplacian, the matrix for which we will compute the eigenvalues. So let A be whatever matrix it is, and let that be the ideal case we hoped it would be mathematically. And H is also another matrix of the same dimension, and they are symmetric matrices such that the Frobenius norm of H is small, which means the real case A tilde, approximate A or A tilde, is actually A plus H, which is a perturbation of A. Okay, so small here and there, some edges extra added, maybe some entries are slightly different, etc., etc. Some edges are deleted and stuff like that, whatever it is, something like that. Then let S1 be an interval. So interval in our case would mean, uh, in the ideal case, we were looking at how many how many eigenvectors are there for the eigenvalue 0. Here we will look at an interval which is small enough. So you want the eigenvalues to be close enough and so on. So let S1 be an interval and sigma S1A be the set of eigenvalues of A contained in S1. So which means these are the set of eigenvalues of A which are within the interval S1. And V1 is the eigenspace corresponding to all these eigenvalues. You know what is an eigenspace? The eigenspace is essentially, suppose you have one particular eigenvalue with exactly multiplicity 1 and one eigenvector, right? So then that eigenvector, the span of that eigenvector, which is essentially like a line, right? I mean, in our intuitive scenario, it's a line. So that is the eigenspace. So then the eigenspace has dimension 1. But suppose you consider two eigenvalues and you want to talk about the eigenspace of those two eigenvalues, then you are actually talking about at least two eigenvectors. So, and these two eigenvectors are again in this particular symmetric case and so on, they're orthogonal, so they will anyway form a basis. So you are actually having a subspace of a higher dimension. If eigenvalues have multiplicity more than one, then eigenspace of one particular eigenvalue may actually have also dimension more than one. So essentially what we are saying is V1 be the eigenspace corresponding to all these eigenvalues which are within this interval, okay, which are close to each other within this interval. And similarly, for the perturbed case also, we can define sigma S1 A tilde and V1 tilde, right? So we can just define the same things for this matrix A tilde. Okay. Then, if the distance between S1 and the spectrum of a outside S1, that means what is spectrum? The range of eigenvalues, right? So basically the eigenvalues. Okay. So the distance of the interval and the eigenvalues outside the interval is given by this delta, which is the minimum. So the what is the eigenvalue closest to this interval but outside this interval? Okay, so which is the nearest but outside member? So that is minimum of lambda minus s, where lambda is an eigenvalue but not in S, and S is within our set of eigenvalues, or say actually this interval, any point in the interval. So how close are the other eigenvalues from this interval? Then the distance of this eigenspace V1 and eigenspace V1 tilde, we'll talk about this notation later, is bounded by norm of H divided by delta. So, which means, first of all, let's look at this. So H, norm of H, we said H is a perturbation. So obviously H shouldn't be too large. So norm of H should be kind of small. And delta, the bigger the delta, the better, right? So it is better if the other eigenvalues are actually far apart. So if you have a group of eigenvalues close to each other within this interval, and there is no other eigenvalue close to these, so then the delta will be bigger. So then your norm H by delta is going to be actually small, right? So then the distance between two subspaces is bounded above. Now, the distance between two subspaces. Okay, so we'll not go into the discussion of this, but this particular theta is actually a diagonal matrix, and the entries of the theta are the canonical angles between the subspaces V1 and V2. Okay, what I'll just tell you the intuition behind this. So suppose these subspaces are just one-dimensional subspaces. Suppose you are only considering one eigenvalue. In this case, of course, not V1 and V2, in this case, V1 and V1 tilde. So the first eigenvalue or second eigenvalue or whatever for A and A tilde, right? So suppose you are only considering this, how much has the eigenspace changed? Okay, so the angle between that is your one particular angle, one canonical angle. If you have a multi-dimension, if you have a higher dimensional eigenspace, then you can actually define the angles in the corresponding way. So you can basically, you have to of course order them properly based on the singular values and so on of to the subspaces, but you can actually define the angles, the first dimension to first dimension, second dimension, and so on of the subspaces. And then you can actually construct a matrix where the diagonal entries are the angles, actually the cos theta, and then this whole sign is actually basically the norm of this matrix is one way of defining distance or distortion of subspaces. So subspace to space, how do you define a distance, right? They're not point to point or something. So this is actually one of the ways people do it. Now, given this mathematical statement, how do we interpret this? Okay, so in our case, we are interested in the application. In our case, what it means is the following. We assume that the ideal graph should have been disconnected and divided into a few disjoint components or communities. But in the real case, there will be some edges across communities, right? So that's the perturbation. But it should be small with respect to the whole structure. Obviously, if we work with a graph of 10 edges or 10 nodes and 12 nodes and things like that, and if we add 6, 7 more edges across communities, it's actually a big perturbation. So we'll not do that. But in a huge graph, okay, some edges across communities and so on, that's actually a perturbation. If we compute the eigenvalues of the Laplacian after the perturbation or after the, I mean, basically, we never have the ideal graph, right? We start with the real case. So if we compute the eigenvalues of the Laplacian, we'll still get several eigenvalues near zero. The in the ideal case would have been that if there are ideally, let's say, k distinct components, k disjoint components, then there should have been eigenvalue. The multiplicity of the eigenvalue should have been k. Eigenvalue 0 should have been k, or you can say the 0 eigenvalue appears k times. Uh, Here, what we expect is we'll still get so many appearances of eigenvalues near zero, same interval. Okay. And the number of such eigenvalues should be hopefully equal to the number of such high level clusters that should have been there. Okay. And after that, there should be a gap in the magnitude of the eigenvalues. Okay. So that is called the eigengap. We'll actually work it out with real examples and toy examples as well. So then if we have that, then the spectral clustering algorithm will go in the following. Okay, maybe because before we go into this, let's actually have a look at let's do the hands-on for some time. Let's get a feeling of what's happening, and then I'll come back to this slide again to tell you the algorithm, and then we'll probably look at it again back. All right, so let me go to the hands-on. Okay, someone asked, is delta is the eigengap? Yes, delta is the eigengap, right? So delta is a formal way of defining the eigengap here. Right.
Sir,
So
why you are want to perturb the graph?
just a moment. I'll just get there. Just a moment. Let me just open this thing. Okay. So the question is why we want to perturb the graph. No, we don't perturb the graph. Um, we work with the real graph. The assumption is that there could be an ideal graph which would have had the communities totally disjoint. But we don't have that. So the real graph is assumed to be a perturbation of the ideal graph. Is it clear?
Okay, sir.
So we do not perturb anything. What we work with is the noisy or the real or the perturbed world. So the ideal world doesn't exist, but we can do the math in the ideal world better, right? Then the perturbation theory provides us the bridge. The math is very clean in the ideal world and easy. The perturbation theory says, well, if you perturb it a little bit, as long as the norm of the perturbation is not so much, your eigenvalues and etc. will not change so much. Okay. All right. So let's get started with this hands-on thing. Can you see is it big enough, the font?
Yes, sir.
All right.
Yes, yes.
Okay. So let me restart the kernel. And I think all cells are anyway clear. All right, so these are just some functions for plotting points. So I will not go into the code of this. You can have a look at it later. It can be done in better ways, I'm pretty sure. So what we'll do, we'll first examine the spectrum or the eigenvalues of a toy graph, which is partitioned into a few disjoint components. I mean, I made the graph. Then we'll change the graph slightly. Okay, slightly. Change the graph slightly. Okay. And then we'll see how the eigenvalues change and what happens. And then finally, we'll actually work with a real graph from our downloaded data set. Okay. Oh. So let's look at a graph with three disjoint components. Here, I'm not drawing the graph here, but you can clearly see what the graph means. This is the adjacency matrix. So the diagonals are all 0. Essentially, the first three nodes, they are all connected to each other, right? And in this case, I'm starting with an unweighted graph or weight equal to 1 for everything. Then the next 5 are again all connected to each other. And the next 4 are again all connected to each other. So the structure of the graph is very clear, right? So it clearly looks like a block here, and a block here. Okay. All right. So now what we can do is, let's just, since we are doing this slowly, let's just also, yeah, let's just also quickly see what my degree matrix looks like. The degree matrix is this, right? So the first 3 have degree 2, the next 5 have degree 4, and the next 4 have degree 3. Okay. And similarly, if you print the Laplacian, yeah, you're going to get again block Laplacians, like this is L1, L2, L3 kind of block Laplacian. Okay. At any point of time, please stop me if you have any doubts, but at this point, these things are very easy anyway. So now, obviously, what we're going to do, we're going to compute let me take this down. Let's actually, yeah, I'm going to compute the eigen values and eigenvectors of this. And for this, the H is it's special for the symmetric or Hermitian matrices. It's a bit faster than if you simply do I. So if I simply do that, okay, it's done. And then I plot the eigenvalues as well as I print them. Okay. So as well as I print the eigenvectors. Okay. So this is a matrix 12 cross 12 matrix. There are 3 disjoint components, right? Clearly 3 disjoint components. So this is one of our ideal matrices which do not exist in real life. Okay. So 3 disjoint components, and you see the 0 appears 3 times, right? So eigenvalue 0 appears 3 times, and then we have things like this. So we will investigate these. So there was a question last time, what happens to the other eigenvalues? Why are they there, and what will happen? We'll investigate these in a while. But let's also look at the eigenvectors here. Let's just examine the first eigenvector. You can see 0 in the first. So the blocks, there are 3 blocks, right? So blocks of size 3, 5, and 4. 0 and 0 in the first and third block, but they have entries in the second block only. So you remember from the last class that if we have block matrices, there will be this constant and 0 blocks, and constant and 0 blocks, and constant and 0 blocks, right? So you see the first 3 eigenvectors cleanly correspond to the 0 eigenvalues. All right. So first 3 eigenvectors cleanly correspond to 0 eigenvalues, and the first 3 eigenvectors are non-zero. They all have unit norm, but they are all orthogonal as well. So they're corresponding to the 3 eigenvalues. Now, observations. So since the graph has 3 connected components, the eigenvalue 0 has multiplicity 3. Fine. We figured last time that if the graph has only one connected component, that means it's a connected graph, then the eigenvalue 0 will have multiplicity 1 only. So the corresponding eigenvectors are constant vectors within the respective blocks. And you can see that if you simply look at these 3 eigenvectors, so last time what we did, we looked at the second eigenvector. We looked at the second eigenvector and we figured that we can actually partition the graph into 2 different parts, but the graph was actually not completely disjoint. Here, obviously, it's pretty easy to see that these 3 eigenvectors clearly give you a partition of the graph into 3 different components, right? So we can simply take the row vectors. So this is the first node, this is the second node, this is the third node, this is the fourth node, and so on. So if we take the first three eigenvectors and construct that as a matrix V3 and take the transpose of V3, right? Then we'll get a 3 cross 12 matrix, and then it gives us a very clean partition. Okay. So essentially what happens, the 12 nodes are mapped to 3 points along the 3 axes according to the cluster they belong to. If we simply do that, if we plot, okay, here, now it's here, observation, and then plot. If we plot, then what happens? 3 points go to, well, not, I don't know. So this is your vector now. This is your matrix now. This is the first node, second node, third node. They should go to 0.5, 0, 0. Second dimension, you have a 0.5. Second dimension 0.5. Which one is that? Is it second dimension 0.5 is, okay, it's, I forgot to label them. Probably this, yes, it should look like this, I think. Yeah, 0 here and 0 here. Yeah. So this is the collapsed version of the first 3 nodes and so on, right? So you see, they are actually mapped to 3 different points, and then it is very easy to cluster them using any Euclidean, any clustering algorithm you learned in the Euclidean space. I mean, k-means. Use k-means. And you know what the k is here, right? So because you are choosing how many vectors to take. So is this part clear, right? So this is the ideal case, and this is very clean. So there is really, it's just reconfirming what we were obviously expecting. Now let's do a little bit of perturbation. Now let's be a bit careful. Let's perturb it only slightly. So what I'm doing is the nodes 0 to 2, they were the first block. So I'm adding an edge from there to the second block, also adding an edge from the first block to the third block, and the second block to the third block. So I'm basically making the graph fully connected now. As I add each edge, I'm also adding the other, I mean, the other side edge, make it symmetric. As of now, of course, I started with a graph with all weights equal to 1. Let's only perturb it a little bit. And these edges are just point on, and let's see what happens. And then we can think about perturbation. I mean, little bit of more real perturbation kind of a thing. So if we do that, and then we do again an eigenvalue decomposition using this A1 matrix, and then let's see what happens. Now, your eigenvalues, I have also printed them. Obviously, the first eigenvalue will still be 0 because it's a connected, I mean, it's a this symmetric graph and so on. So this will be 0, that's fine. But the second eigenvalue and third eigenvalue are also pretty close to 0, but they're not 0 anymore. It's a positive one. It's a positive one, but they're not 0 anymore. And the third one is also not 0 anymore, but it's a positive one, but pretty small. So you see the picture still looks pretty much the same. They're just slightly perturbed. You see there is another group of eigenvalues nearing 3, another group of eigenvalues near 4, another group of eigenvalues near 5. So that's a mystery still. We will look at that a little bit later. What do these people mean? But what we know now is we can still do the same clustering using the first 3 eigenvalues. And this is our eigengap, right? So this is our, interval, right? 0 to 0.1, let's say, or 0.09. So this is our interval S1. And this is a huge eigengap relatively, right? So as soon as we know that there is a big gap, we know that our one level clustering, the highest level clustering, we can take the first 3 eigenvalues and first 3 eigenvectors. Let's look at the first 3 eigenvectors. The first eigenvector, now that the graph is connected, is all constant. So that does not differentiate between the nodes at all. So this is useless. The first eigenvector is useless. Agree? Right? So this is going to be same. So that's useless. But what about the second and third? In the last class, we talked about the second eigenvector when the graph was seemingly a collection of 2 disjoint components. But here, there are like 3 components with little bit of edges from here and there. So we should expect that the second and third eigenvectors should give us the clustering. Well, it does. So now let's look at this. Obviously, the first eigenvalue has multiplicity 1, okay? But we can either inspect the numbers here, or we can actually plot them. So what about the case if we simply plot? If we simply plot uh, the this much of the matrix, right? So the up to 3 eigenvectors, okay? Just like before, if we simply plot that, and then we see that okay, they are not the points are not collapsed onto each other, but they're like this. But that's not such a good plot. Because I said that the first eigenvector is actually useless, we can actually plot it on 2D. We can plot it on 2D, and let me put labels equal to 2. Okay, actually looks bad, but anyway, this is not a good code that I wrote for putting the labels. But you see that 3 points are here, 3 points are here, and no, not 3. So 3 points. No, false was better. You can see that 3 points are here, maybe more than 3 points are here, and so 3, 4, 5 should be the division essentially. So what you see here is that the second and third eigenvector, so the Eigen space will have dimension 2, right? So that's why we are happy with the 2-dimensional plot here. They will actually be enough to partition our nodes into 3 disjoint components as I wanted. If we just look at it also, it's pretty clear that all these are like minus 0.1 and plus 0.5. They're all like the 0.3 something and minus 0.1, and they're minus 0.3 and minus 0.25 or around something like that. So these points are similar. All right, any question as of now? Okay, so things
Sir,
are
again, can you again repeat why we took the third eigenvector? I mean, we could have done this using only the second eigenvector also.
Right. So last time what we did was we assumed that we are going to cluster the graph into 2 partitions only. Okay. So we assume that we're going to cluster the graph into 2 partitions only, and then we took the second eigenvector only. And the example we saw also, it was actually a graph with, I mean, the reasonable partition would have been 2 partitions to start with. Now, in this case, our graph has 3 partitions, or
so that's
almost like a 3 partitions. But how do we know we have 3 partitions? I mean, looking at a huge graph, we cannot say there are 3 partitions, right? This was our handmade example. But we can see from here. If you just look at the slides from the last class, I mean, we can also look at it a little bit later. We have to go back and forth a bit. You can see that the eigenvalues had a gap after 2. Here we have a gap after 3, right? So 3 partitions, 2 dimensions will these two, basically the first one is useless. Otherwise we can also take the first one. We can plot them into this 3D. So since we have 3 eigenvalues close to each other, we can kind of assume safely using the perturbation theory that looks like this graph should have 3 partitions. Okay, and then we can actually use that to make the 3 partitions. How? These are our points, right? These are our points. And what I did here, I just ignored the first eigenvector because that doesn't give us anything. But if you simply go with that also, your graph is now translated or mapped into this 3D space, 3D Euclidean space, with the points being in these 3 different places. You can partition them. You can use your k-means algorithm, right? So that's what it has done. Now let's actually do a little bit of more thing here. So why don't we actually make them edges and see? Obviously the perturbation should then become higher, right? Okay, so let's do that. And then we see that the perturbation is slightly higher, but still we have a gap, right? So as you perturb it more and more and more, your gap will not be so clearly pronounced anymore. But well, obviously the structure should remain, otherwise it doesn't make sense to do it. So in a real case, the assumption is that, well, there will be a gap. So we will actually see that also. So this is a bit more perturbation. There is a bit more of gap, but still you can say that this is your first level of clustering. So I'm talking about first level of clustering. Let me actually do this. Yeah. So now you see the points are not collapsed like before, but still you can see three different clusters here, right? You can still see three different clusters. Now, what happens if you don't want to cluster into three different clusters, rather you want to cluster into two different clusters? Then maybe you will put these five into one and these three into one. Well, that's your choice. But here the eigengap clearly tells you that you should use three clusters to start with. Now, what about the next eigenvectors? What happens after that? So to do that, let me actually again go back to our original perturbation, which is a small one that will help us understand it. So this is the small perturbation. Now we see that there are three eigenvalues in the first level, two in the second, and three in the third, and four in the fourth level, right? Let's look at the eigenvectors after the third one. And let me just, since I have done this examination before, let me just only look at the first. So these three, so you know these two eigenvectors, but only the first three rows. That means the first three nodes. Now the first one, -4 1 7 1, -4 3, -7, and +8 1, and this is almost like a 0. So you see that the fourth eigenvector actually separates the nodes of the first community. You know, they are pretty separate now. So if you simply plot them, if we simply yeah, so this is our thing now. Yeah, if we simply plot the fourth and fifth columns, right, then the first node corresponds to this, the second node is this, the third node is this, and now you can see the difference between them. So gives you an option of further hierarchical kind of a clustering, right? So once you have done one level of community detection, if you want to go deeper, you can actually do this. Similarly, if you simply examine the eigenvectors further, you will see that we have something like this, right? So the next three will actually separate out the last block. The last block, there are four nodes. So next three will actually separate out the last block. So the next three are 1, 2, 3, 4, 5. See, next three are here mostly 0, here mostly 0. Here we have some entries, right? So this portion that will separate to the last block, and these four will actually separate out the middle block. Okay, so essentially in each case, these, so as these eigenvalues, as you take more and more eigenvalues, what happens if you take all eigenvalues and run k-means? Then every data point is different, right? So then each of these are normal vectors. They are basically orthogonal, right? So with this is eigenvector set, eigenvectors that will form a basis and so on. So then they are actually totally different. So this also gives you an option of somewhat hierarchical clustering, level by level, if you want it that way. Any question as of now? Okay, so now let me quickly then revise what I said about the slide. I said, okay, we'll come back to the slide just a bit, and then we'll go back again to the hands-on, and we'll try this with a real data set. Essentially, what we did, we have an n cross n weighted adjacency matrix. So not the ideal one. We'll start with a real matrix, whatever we get in the data. The algorithm will be like the following. We compute L. Now this L we have learned is the degree matrix minus the adjacency matrix. This is called the unnormalized Laplacian. There are other variants. There are actually multiple other variants which are called unnormalized Laplacians. So we're not going into that, but yeah, so it's like d power minus half L d power half. So basically you normalize the Laplacians in some way. Okay, so there are other variants. The same structure of the algorithm or the skeleton will follow, where some other people have made improvements using slightly different variants here and there. So the basic structure is like this. You compute the unnormalized Laplacian, compute the first, which means the smallest k eigenvalues and corresponding eigenvectors of L. Now you don't know k beforehand, so you should compute large enough k. But if your graph is huge, you don't want to compute all eigenvalues. So you compute some k so that you can see some gap somewhere, right? So that's the idea. So let V be the n cross k matrix. So now I'm totally skipping the idea of the gap in this description, but the idea is, well, you compute the k eigenvalues after which there will be a gap. So in practice, what you have to do, you have to do k plus something eigenvalue so that you see a gap after k. So assuming you know where the gap is, you can just work with k eigenvalues or k eigenvectors. So let then V is our n cross k matrix obtained by stacking the k eigenvectors, the first k eigenvectors. Okay. And we can compute V transpose, which is in a k cross n matrix. And then the ith column of V transpose will correspond to the ith node of the graph, just like we did in our hands-on. You can discard the first eigenvector if you want, because that is going to be constant. It's not going to give you any value. There are other variants to this. So instead of taking V transpose simply, you take V transpose and then normalize each row, normalize row of a V, or normalize each column of V transpose and things like that, so that all the vectors have unit norm and stuff like that. And then cluster the points using the k-means algorithm. This is Euclidean space already. So you can actually cluster them using k-means. Also, because you know what your k should be, right? You clearly know what your k should be. This is actually a very good way of doing it. Okay, so now let's actually try to make some progress on that, on some real data again in the same place, obviously. Yeah. Okay, so we did this, yes. So now experimenting with a real data set. This is from the Stanford Network Analysis Project. The links are there. I just downloaded this. This is a so this data set is not very big, so it's easy to work for a hands-on like this quickly. So there are about 4,000 nodes and 88,000 undirected edges. So let's just do that. Yeah. So this is this, and then we will get the adjacency matrix of the graph. Now here in the data set, they mention that it's an undirected graph. So whenever they put a node, whenever they put an edge between 0 and 2, 0 and 3, they don't actually put an edge between 3 and 0. So I'll have to manually do that, or rather I have to write some code to do that.
Sir, how is the data prepared in this case? Original data?
Oh, that I don't know. We can actually look at this website. So let me quickly. So let me just read this a bit. The dataset consists of circles or friend lists from Facebook, was collected from survey participants using the Facebook app. Okay. Maybe there are people. Yeah. So basically, there is a paper on this also, right? So there probably you should get more details. My goal was here just to get some real data with people and friends and things like that. So I didn't, as of now, bother to do that. But yeah, I mean, you can actually have a look at it. So they also say how many nodes, how many edges, nodes in the largest, probably WCC is something community, and then average clustering coefficient, number of triangles, it's quite large, etc., etc. Fraction of closed triangles. Okay, closed triangles, we haven't really talked about that. Then diameter, longest, shortest path. So basically, they have several more information on this, and the data. Hold on. Yeah. So this Facebook combined.txt, this is the file I'm using, but the star.gz, there are lots of ego network and many other different things are there. So if you download, you can actually use them. All right. So our goal is basically just the graph. here I simply use the standard way of doing this. So maybe I'm actually missing an edge here because of the way I read it, but doesn't matter. The file actually doesn't have a header. Maybe Panda actually assumes there is, but that can be changed. It shouldn't really matter one edge. Okay, and then by the way, here you have to mention the shape because otherwise your graph will be 4032 times 4039, so it will not be full, it will not be square. And then I'm actually forcing it to be a symmetric graph, right? Forcing it to a symmetric graph and actually checking that the matrix is symmetric. So it doesn't print anything here, so the matrix is actually symmetric. So because the weight there is, it's an unweighted, but anyway the graph is said to be undirected, so it doesn't actually put the reverse edges. Now we will compute the eigenvalues and eigenvectors of the Laplacian, and basically we want to examine the spectrum. That is our main goal. Now here one point to note, which library to use. There are lots of them. So scikit-learn actually has, so the sparse matrices and so on, it's easy to use this CSR or CSC matrices from scikit-learn. And for our first thing, we used IH from NumPy linear algebra library. Now, scikit-learn also has ISH, sparse Hermitian. Okay, but when I tried that, it was pretty slow. The reason is it uses this ARPAC library, probably C or something, and that is not so good for the smallest eigenvalue side. Here, so if you want to use this for SVD kind of thing, this will actually be pretty fast. If you want the largest eigenvalue onwards, it will be pretty fast, but the smallest eigenvalue side, it's not pretty good. So, so what we do is, yeah, so we compute the, oh, what happened here? That didn't happen before. Let me check. Ah, some problem. A is this. What is my A? I did. Yeah, A is this.
Sir, what is D here?
Ah, yeah, right. I did
L
not.
equal
I did not do the D part, right? So degrees. So this is the D. Yeah. I think when I was just doing some code manipulation here and there. Yeah, this worked fine. So so this is also a bit complicated here. You may run into trouble if you do this for the first time. It's a sparse matrix, so you do A dot sum and then give the axis. In this case, it will not make a difference whether you give axis equal to 0 or 1 because it is symmetric. But then making the diagonal from here, it's an offset actually. Here you simply want the diagonal. So offset 0 is fine. But yeah, so you just have to make this into an array. Otherwise, this is actually a matrix object and you will have trouble here. So I think that's what I had initially, and then I was.
Sir, what is the, why are you using diags instead of np.diag? I mean,
oh, because I am still in the sparse space.
okay, so we have different
Yeah,
treatment
it's a
for
bit
the
different
sparse.
thing. It's a bit different.
Yeah.
So I was initially hoping that we will do well with the sparse matrices all the way, but as it turns out, for this matrices of this size, the sparseness does not matter. I mean, 4,000 times 4,000 will fit in the memory of any laptop, so it shouldn't matter really. But I initially thought that will be faster. But anyway, so you can convert this into a dense matrix here itself and then change the code. It should not make a difference. Okay, so L D minus A, and then I do, but here what I do, I said this one ISH, and then I can provide a K, and then I can provide smallest magnitude. That means you start from the smaller one and so on. And I tried different options, and then I read up, and we figured that it will not actually be faster than this. So for matrices of this size, which totally fits in memory, this is very fast, and this is actually complete eigenvalue calculation, whereas even for k equal to 100, it would have taken a lot of time with this one. So anyway, so let's not worry about this dense or sparse thing right now. Our main goal is this thing, right? So what if we plot? So let's plot. So this is a real graph, and when we plot, what we see is something like this. Okay, now let's zoom in a bit, right? So this is not enough. Let's zoom in a bit. So let's plot the first 10. Now you see that the first 10 itself, first 6, 7 actually, first 7. So first 7, there is a gap here, right? What about 20? Yeah, so you see first 7 and there is a gap, and then there are a few here, and then this maybe 50. Okay, so first 7, there is a gap, and then we have this whole line here, and this will actually go on for more than 100, I think. Yeah, so this is our 7, 8, 9, 10, 11th to maybe 90th or something, and then it kind of, again there are some gaps. If you actually zoom in, you will see this and this and so on. But we are actually we'll be happy with this huge gap to start with, right? So from here, your immediate observation is that this graph, if you take the first 7 eigenvectors, discard the first one because it is non-informative. Okay, it's a connected graph, right? So it's a connected graph. The first eigenvalue is 0, but no other eigenvalue is 0. That's a proof that it's a connected graph. Then if we take the first 7 eigenvectors, forget the first one, so then the second to 7th eigenvector, and if we use them to do a k-means kind of clustering, I have not done that here, but you can actually complete that part of the code. Then you are going to get a reasonable clustering. Okay, now it's actually an interesting thing to investigate. Why do we have this huge multiplicity of eigenvalue equal to 1 here? That is not very clear from this, but there will be around 7 clusters to start with. Then a few more clusters. You may also take around 7 or 8 or 9. Probably the result should not be too different, but there are ways to compute how good the clusters are and so on. So I believe if you take 7, it will give you a pretty good thing. Then, however, if you want to do a deeper clustering, you should actually take something like up to this many, right? So if you take 120 or something like that, then again there are some gaps and things like that. So obviously, social network graphs, also this graph is just a subset of a Facebook graph and all that, right? So it's not the question, how is it constructed? How did they choose the nodes? It's a survey. So, well, it may not actually be a proper representation of a social network, but you can see it's still a real graph, it's still connected, and still we can see the communities from this. So if you want, you can try this out with other kinds of real social network data. Anything of the range of 10,000 nodes you can easily run on your laptops. Larger ones may be slightly difficult. Yeah, question.
So what is the reason for that linear line? I mean, first we see that
so
the
what it means is that, so this linear line means, so what did it mean in this case, for example? In this case also we had linear lines, right?
It represents one of the cluster.
It represents one of the clusters. So here the first line was essentially dividing the graph into different clusters. The second line was one cluster. The third line was another cluster, and so on. If you go up to this, then that cluster will also get divided, right? So the linear line here is one huge cluster, and then again you have some more, but the distinction between these lines are not so clear anymore, right? So that is basically the thing. So it may be that this particular graph, in reality, in many cases, you will not have such a huge line. But if you actually draw up to 4,000, then you will see it's pretty. I mean, you don't really see the gaps anymore there. But how about, let's say, 1,000 to 1,500? Ooh. No, sorry. Okay, so you don't really see the gaps there anymore. So what about 100 to 500? Yeah, see, you have some such cluster kind of thing. But if you go very, very deep, you don't really get to cluster them so much. Okay, any question? So let me, for the sake of completeness, let's make this. Yeah. Yeah.
So do you always take like the first k eigenvectors, something like this, looking at the picture, or we can choose which eigenvectors to take? Like for example,
No,
corresponding.
of course not looking at the picture, but it should be an automated system, right? So the automated system, you can implement what we are interpreting here. What are we interpreting here? This is an interval, right? This is an interval. The gap from this interval to others is pretty large. You can have some thresholds to implement that to detect it automatically, right? So you can have some parameters to detect your threshold. Obviously, there may be decision points where, suppose you don't actually have a proper eigengap, then what do you do, right? Then one of the insights from that is, well, the graph is difficult to cluster into clearly distinguishable communities. So that's one of the insights. But still, if you have to do it, you will have to choose something. So what you can keep doing is you can keep computing the individual eigengaps. And whenever there's a bigger gap, suddenly there is a jump. You note that. And you do that for, first few hundred maybe. And then so that will give you some kind of numbers from which you can detect where is the best gap that you are looking at. But your question was also something else.
No, sir.
This is what it is. Yeah. So looking at is just what we are doing now, but you can actually implement this, using some parameters. So that's basically the point.
Sir, is this values? The eigenvalue is less than 0.2, right?
Right.
The one we considering.
Right.
So this number gives is this number gives a quality of the clustering or that kind of thing?
That actually I don't know. So in a way, if you look at our original ideal matrix, right? In the original ideal matrix, they're all 0. In the perturbed matrix, they are slightly more than 0, but I perturbed very little. So they are slightly more than 0. If I perturb a little bit more, then they will be slightly higher, right? So what it kind of tells you is how much perturbed your matrix is from clearly disjoint communities. But the quality of the cluster is very subjective, right? Very subjective depending on your goal. So there are obviously measures for quality of clusters. So, but that depends on your goal. So I don't know whether this number, so the highest one that you are taking, so essentially what you are doing here, you are assuming that this number, which may be 0.18 or something, is a perturbation of 0. Right, you are assuming that this curve should have actually been a flat 0. So this is your perturbation. So, but then in a real social network case or anything of this type, you are okay with the perturbation, right? You actually want that to happen because that's the real case. So this may not be the quality of the cluster. However, the gap will tell you the boundary also, right? So essentially, this is your gap delta, right? This is the gap delta. If the delta is pretty large, then what you have is the ideal eigenspace to this eigenspace, it's almost the same, right? So that's basically the idea. However, in real applications, whenever you are clustering into communities, there are lots of things to consider. How deep do you want to go? Are you happy with 7 clusters in a graph of 4,000, or do you want to have more? And so many other things to consider here, right? So, so based on all this, you will have to devise a strategy to decide your clustering. Okay. Any other question? So what you can do is,
sir, I have a confusion. If I consider 7 point, is that means that we get 7 cluster? isn't it the dimension of the
It should be the dimension of the eigenspace, yes.
Yeah.
But
So
look, I mean, in most cases, it will. I mean, there is no multiplicity here, right? So multiplicity is all one only. So there is no repeating eigenvalue here. So dimensional, the eigenspace will actually have 7 dimensions.
yeah, I mean, the number of cluster can be larger than 7, right? Or
Okay,
if,
okay. So you can actually run k-means with any k here. You can take your first 7 eigenvectors and run k-means with any k. But as we saw, if you take k equal to 7, it will give you the nicest kind of clusters.
okay.
Right. So that is from these vectors. However, if you don't have these nice gaps, then the whole problem is a bit more different and it's difficult also. Okay, all right. So some exercise for you, optional, but voluntary. I believe you have found this pretty interesting, some of you at least. Download other real data sets. Okay. Unless you take real data, you will not feel what kind of gaps exist. So download other real network data sets and simply run this piece of code, okay? Or write your own piece of code, it's only a few lines, and see what kind of eigengaps do you have, and maybe finish this by calling k-means using one of the libraries, and then compute the quality of the clusters using some measure.
Sir, so my question was, is the number of 0 eigenvalues a better representative for the number of clusters than the eigengap, than the number of eigenvalues before the first significant eigengap?
Okay, so our original basic clean mathematical theorem was, is the number of 0 eigenvalues is 5, then there are 5 clearly disjoint components. Now, what happens if you have 5 zeros and then another 10 nearly 0 and then a huge gap? Then of course you should take all 15. Right. So that's a more natural way to go about it.
Yeah, so I mean, eigengap is a much better measure.
Eigengap is a much better measure, not whether they are exactly 0 or very close to 0. They are kind of okay. I mean, they're all the same. However, if the eigenvalues kind of increase hugely, so suppose let's look at this picture in this. Okay, so suppose the picture was something like this. Instead of this flat line here, suppose I had a line upwards like this, and then there was an eigengap. Now there it becomes a bit more complicated. Or there is some around 0, then there is a small gap, then it goes up, then there's a large gap. Okay, so those cases are more complicated, and there may be multiple ways of doing reasonable clustering. So then your decision problem is a more difficult one, and then it depends actually on what is your application demanding. Does it demand big clusters, small number of clusters but big ones, or does it demand more hierarchical approach? So there are all these tools around here, and how they correspond to the clusters and so on. So you will have to actually choose them if you in the real application. Okay, all right. So I just want to just a moment. Yeah. So I think let me stop the recording. We are done. There is somebody in the chat. Oh, you only asked me the question, right? So fine. Yeah. Do not write in the chat because I cannot see it sometimes. So just speak out. All right. So I'm stopping the recording.